Landing on the moon remains one of the toughest feats in space exploration. Even after decades of missions, it's a challenge that continues to test the limits of our engineering and ingenuity. Despite our technological leaps, the moon's challenges haven't changed. The environment is as harsh and unforgiving as ever, and every new mission must contend with the same relentless obstacles that faced the Apollo astronauts. There's no atmosphere for parachutes, so landers must rely on rockets to slow down at exactly the right moment. The timing and precision required are extraordinary, leaving no room for error as the spacecraft hurtles toward the surface. The surface is unpredictable. Craters, boulders, and steep slopes everywhere. Each landing site is a minefield of hazards, and even the most detailed maps can't reveal every hidden danger. Finding a safe spot is like parking in a field of boulders, blindfolded. The lander must scan and analyze the terrain in real time, searching for a patch of ground flat and stable enough to touch down. Moon dust, or regolith, is sharp and abrasive, kicked up by rocket engines and threatening to damage sensors and instruments. This fine dust can obscure cameras, clog machinery, and even pose a risk to future astronauts. Even with years of planning and advanced simulations, the final descent is a high-stakes moment. Every second counts, and the tension in mission control is palpable as the lander approaches the surface. The lander is on its own, making split-second decisions based on its sensors. Autonomous systems must react instantly to unexpected obstacles or changes in the landing zone. A single faulty reading or software bug can doom the mission. There's no second chance. Every system must work perfectly, or years of effort can be lost in an instant. That's why every successful landing is still a major achievement. It's a testament to the dedication and expertise of everyone involved, from engineers to scientists to mission controllers. Recent missions from around the world have struggled, proving how unforgiving the moon can be. Even the most advanced nations have faced setbacks and hard lessons. Each attempt's success or failure pushes our technology and teaches us something new. Every mission adds to our knowledge, helping us prepare for the next challenge. The moon continues to demand our best ideas and efforts. It inspires innovation, teamwork, and a relentless drive to overcome the unknown. That's what keeps lunar exploration so exciting and why the next landing will be just as thrilling as the first. In recent years, a surprising number of robotic moon landings have ended in failure, even though they use some of the most advanced technology ever built for space exploration. The dream of a smooth, autonomous lunar touchdown remains elusive, and each new attempt brings its own set of challenges. Take Japan's Hakuto R lander, for example. It crashed when its sensors misjudged its altitude, causing the spacecraft to think it was closer to the surface than it really was. In the final moments, the lander simply ran out of time and fuel to correct its mistake. The American Peregrine lander faced a different problem, a propellant leak that doomed the mission before it could even attempt a landing. Even the smallest malfunction can have catastrophic consequences in the harsh environment of space. But many failures ultimately come down to the lander not fully understanding its situation. The moon's surface is unpredictable, and the lander must interpret a flood of data in real time. These spacecraft rely on a complex suite of sensors, lasers, radar, and inertial measurement units, to figure out exactly where they are and how fast they're moving as they descend. If any sensor gives bad data, or if the readings don't match up, the onboard computer can make a fatal mistake in just seconds. The software is the lander's brain, making rapid-fire decisions with no room for error. It must process information and react instantly, with no chance to call home for help. Even a tiny bug in the code can mean disaster, as with Hakuto R's software, which wasn't prepared for unexpected sensor readings. One overlooked scenario can spell the end of a mission. Despite faster computers and better sensors, the core challenge remains. Landing autonomously on the moon is still incredibly hard, and the margin for error is razor thin. Robots must perform complex maneuvers entirely on their own, millions of miles from help, with no second chances if something goes wrong. These failures aren't signs we've forgotten how to land, they're proof of just how tough the test still is, even for the world's best engineers and scientists. Each setback is a lesson, bringing us closer to success. Every failed landing teaches us something new about the moon, our machines, and ourselves. The moon is still the ultimate proving ground for engineering, and every mission, win or lose, pushes the boundaries of what's possible. These problems aren't new. Early lunar missions faced them too. In the 1960s, NASA's Surveyor landers were our first robotic scouts. Surveyor 3, for instance, landed in 1967 but bounced twice because its radar was fooled by the moon's reflective soil. The lander was lucky not to tip over. The moon's surface can trick sensors, reflect radar oddly, and blind cameras with dust. Back then, engineers had to solve these problems with far simpler technology and a lot of ingenuity. The fact that any surveyor landed safely is a testament to their skill. Comparing old and new missions shows that technology alone isn't enough. The moon's gravity, vacuum, and tricky surface haven't changed. The same sensor issues that plagued Surveyor still challenge us today. We need systems that can adapt and understand their environment, not just better hardware. The lessons of the past are still relevant. The moon keeps us humble. So how did Apollo succeed where so many robots have struggled? The answer: humans were in the loop. Apollo astronauts were skilled pilots able to see the surface and take control if needed. During Apollo 11, Neil Armstrong famously took manual control when the computer aimed for a dangerous crater. With seconds of fuel left, he found a safe spot and landed. The partnership between human intuition and computer calculation was Apollo's secret weapon. Astronauts could adapt in real time, something robots still struggle to do. Modern landers must make every decision alone, limited by their programming and sensors. When things go wrong, they can't improvise like a human. Apollo's success shows the value of adaptability and real-time judgment. That's the human edge. After many failures, Firefly Aerospace's Blue Ghost lander finally delivered a win. Its secret? An AI-powered vision system inspired by human pilots. Blue Ghost used cameras and advanced AI to see the lunar surface during descent. The system compared live images to stored maps, a technique called terrain relative navigation. This let the lander pinpoint its position using craters and ridges, not just sensor data. If a sensor gave odd readings, the AI could cross-check with what the cameras saw. This fusion of data made the system robust and reliable. Blue Ghost didn't blindly trust any one sensor. By giving the lander eyes and a smart brain, Firefly recreated the human touch that made Apollo so successful. The result? A confident, safe landing. Blue Ghost's success points to a new path for lunar exploration. Combining AI with traditional systems makes landers smarter and more resilient. Blue Ghost's approach is similar to the technology behind self-driving cars. Both must navigate unpredictable environments without direct human control. Self-driving cars use radar, LiDAR, GPS, and especially cameras with AI to understand their surroundings. The AI processes images to identify obstacles and make decisions, just like Blue Ghost did on the moon. This method, sensor fusion, combines data from multiple sources for reliability. If one sensor fails, others can fill in the gaps. The same principle made Blue Ghost's landing system robust. This crossover shows how advances in one field can help another. AI that helps cars avoid accidents can help landers avoid craters. Blue Ghost's vision-based system is a powerful argument for hybrid approaches. By giving robots the ability to see and interpret their world, we make them safer and more capable. Whether on highways or the moon, this technology is changing what's possible. The future is a shared brain, human-inspired, AI-powered. If AI vision systems are so advanced and effective, why aren't they used everywhere in space exploration? It's a question that sparks heated debate among engineers and scientists. The answer comes down to two powerful forces: risk and tradition. Space missions are incredibly expensive and the stakes are sky high. That's why engineers often rely on flight heritage technology, hardware and software that's already proven itself reliable in the harsh environment of space. This conservative mindset, while understandable, can sometimes slow down the pace of innovation and make it harder for new ideas to take root. New technology, especially AI, is often seen as risky. What if it fails in the unforgiving vacuum of space, far from any help? But recent failures have shown that even tried and true systems aren't always up to the challenge, especially when it comes to the complex task of autonomous lunar landings. The moon's environment is unpredictable and extreme. It demands not just reliability but adaptability and quick thinking from our machines. Blue Ghost's success is a sign that the future of space exploration lies in blending the best of both worlds. Proven, robust hardware with smart, adaptable AI systems. We don't have to abandon the old ways. Instead, we can enhance them, making our spacecraft smarter and more capable. By adding an AI brain, we give landers the ability to handle surprises and make decisions on the fly, while still being dependable. To truly master the moon and push the boundaries of exploration, we must be bold enough to embrace new ideas and technologies. The next era of lunar exploration will be built on this careful balance between tradition and innovation, between caution and courage. That's how we'll land as safely as Apollo did, only this time, we'll do it with robots that can think for themselves.